lecture 4. 4 lectures in, which is equivalent to 4 weeks or a month already of linear algebra. And what I introduced yesterday was the notion of linear independence and linear dependence of vectors. So suppose I let V, this is my vector space Rn, and we have vectors V1, V2 up to V sub k in V. So these vectors are linearly dependent if there exist scalars, numbers, x1, x2 up to x sub k, such that this linear combination x1 v1 plus x2 v2 plus x sub k v sub k, this is some vector in V, is the zero vector, and not all the x sub i's are zero. X sub I is different from zero for at least one or for some I. So if you have a finite set of vectors, or finite sequence of vectors, and some linear combination of them is zero, where not all of the coefficients are zero, those vectors are called linearly dependent. And the vectors are called linearly independent if they're not linearly dependent, or if whenever you have x1 v1 plus xk vk equals 0, then necessarily every coefficient is 0. So for example, if you take v1 equal to, let's say, 2, 3, v2 equal -1, 4, and v3 equal to, say, 1, 10. Let's see if this works. So we ask the question, here are 3 vectors, are they linearly dependent or linearly independent? And if I can choose coordinates right, if I take 2v1 plus 1 times v2 plus 1 times v3, that's 2 times the vector 2, 3, plus 1 times the vector -1, 4, plus 1 times the vector 1, 10. So that's 4, 3 plus -1, sorry, 2 times 2 is 4, 2 times 3 is 6. And maybe I'll make this just to make it more interesting. 9, 30. So this is 2 times 2, 3, plus 1 times -1, 4, plus, let's say, plus -3 times v3. So this, let me do this more neatly. So I picked vectors v1 equals 2, 3, v2 equal the vector -1, 4, and v3 the vector 9, 30. And if I take 2v1 plus v2, that's 1 times v2, minus 3v3, that's 2 times 2, 3, plus v2 minus 1, 4, minus 3 times 9, 30. Oops, let me make this 3 and 10. No, let's just leave it the way it's 330. Make this a third. A third times 330 minus 1/3. So this is 4, 6 plus minus 1, 4 minus 3, 10. And what is this? 4 minus 1 minus 3, 6 plus 4 minus 10. That's 0, 0. So here I have a linear combination of the vectors v1, v2, and v3, which gives the 0 vector. But the coefficients are not all 0. In fact, none of them is 0. So these three vectors are linearly dependent. But if I just took the first two of them, 2, 3, and minus 1, 4, I claim these two vectors are linearly independent. And how will we show that? So suppose some linear combination of these two vectors is the 0 vector. So this is the vector 2x1, 3x1, and this is the vector minus x2, 4x2, which is 2x1 minus x2, 3x1 plus 4x2, and that's the 0 vector. So if some linear combination of these two vectors is 0, that means there's a solution of this vector equation, which is exactly the same as the system of equations 2x1 minus x2 equals 0, 3x1 plus 4x2 equals 0. So we have to solve these equations. The first equation says x2 is 2x1. This equation says that 3x1 is minus 4x2, which is minus 4 times 2x1, which is minus 8x1, which means 11x1 equals 0. So x1 has to be 0. And if x1 is 0, x2 is 0. So this is an algebraic argument to show that the only linear combination of these two vectors that gives the 0 vector is the trivial linear combination with where both coefficients x1 and x2 are 0. So these two vectors are linearly independent. And that's what we talked about yesterday. Let me just check my notes of yesterday's lecture to see how far I got in this section. Okay. So any questions about this? So linearly independent vectors are very important. They have several very nice properties. One is the following. So suppose that v1, v2 up to v sub k, this is a sequence of linearly independent vectors. So suppose we have some linear combination of these vectors, x1, v1, plus x2, v2, and so forth, up to xk, vk. And suppose we have another linear combination of them, y1, v1, plus y2, v2, up to y sub k, v sub k. Right? So if, in fact, these two linear combinations are equal, that is, they give the same vector, this only happens if and only if there's only one possible choice for the coordinates, the coefficients. x1 equals y1, x2 equals y2, and in general, xi equals yi for all I going from 1 up to n. And the proof, so this is in the text, theorem 1.7, the proof is that if these two vectors are equal, then 0, the 0 vector, is the difference. Right? If your two vectors are equal, you subtract one from the other, you get 0. But if I just rearrange this, this is x1 minus y1 times v1, x2 minus y2 times v2, and so forth, up to xk minus y sub k times vk. So this linear combination of the vectors v1 up to vk is 0, and so all of these coefficients have to be 0. xi minus y equals 0, or equivalently, xi equals a yi for all I. So if a sequence of vectors is linearly independent, then a vector is a linear combination of those linearly independent vectors in a unique way. Okay. Let's discuss one more important operation we can perform with vectors. Suppose we take our vector space Rn, let's call it V, and let S be a non-empty subset of V. Suppose we let, I'll write S in brackets, be the set of all linear combinations of vectors in V. Then this set of all linear combinations of vectors in S is a subspace of V. Why is that? So a set W is a subspace of V. This is the definition. If three properties are satisfied, first, the 0 vector is in W. Second, if W1 and W2 are vectors in W, then W1 plus W2 is in W. So the set W is closed under vector addition. And if W is in W and C is a scalar, then C times W is in W. So W is also closed under scalar multiplication. So that's the definition of a subspace. So S is not empty. So we can choose any vector W in S. There is some vector in S. So the scalar 0 times the vector W is in S. But any vector multiplied by 0 is the 0 vector. So the 0 vector is in the set of linear, because this is a linear combination of vectors in S. One vector, one scalar, that's a linear combination. So this set contains the 0 vector. And if W1 and W2 are in this set of linear combinations, I can write W1 as some linear combination of a finite number of elements of S. And I can write W2 as some other linear combination of elements of S, where these V sub i's are all in S. And if I add W1 plus W2, that's just another linear combination of elements of S. So this is in this set. And C times W1, just multiply by the scalar, you get CX1 V1 up to CXK VK. That's also in S. So the set of linear combinations of elements of S is a subspace. It's called the subspace generated by S. And if we let script W be the set of all subspaces W of the vector space V that contain the set S, I claim that if I take the intersection of all these subspaces, I get exactly the subspace generated by S. And the proof goes as follows. First of all, this set, this subspace is a subspace that contains S. So this is in the set W. So the intersection of all vector spaces in W, this is one of them, is contained in this. On the other hand, if S is contained in a subspace W, then W must contain all linear combinations of elements of S. So this subspace is contained in W for all subspaces W in the set script W, which means the subspace is contained in the intersection of all subspaces. So if we put together these two inclusions, they imply the result. And you can also note that this is just a note. If S is the empty set, then S is contained in every subspace, because the empty set is contained in everything. So in particular, S is contained in the trivial subspace that contains just 0. So one could define the subspace generated by the empty set to be 0. That's just a nice observation. Let me prove one more important theorem about subspaces. So this is now page 6 already. Wow. So suppose we let V be Rn. And let S be some set of M vectors, a subset of V consisting of M vectors. And suppose we let W be the subspace generated by S. If we take V1, V2 up to V sub n, this is some sequence of vectors in W, then if n is bigger than m, this is the important condition, we have a subspace generated by a set with m vectors, and we choose n vectors in that subspace, n bigger than m, then these n vectors that we picked must be linearly dependent. And the proof is a very nice proof using a theorem about systems of linear equations. So for all j from 1 to n, if I take the vector vj, I can write it as a linear combination of these m vectors. This is aj1 w1 plus aj2 w2 plus ajm w sub m. So for all j from 1 to n, each of the vectors vj is a linear combination of these m vectors, and I write the coefficients like this. Actually, I should write it the other way. 1j, 2j up to mj. Or if I use sigma notation, this is summation. I goes from 1 to m, a sub I j, w sub I. So this is writing each of these vectors as a linear combination of the m vectors in my set. Suppose I take a linear combination of the vj vectors. I take x1 v1 plus x2 v2 up to xn vn. Or in sigma notation, this is summation. J goes from 1 up to n, x sub j, v sub j. But I can write v sub j in this form. So this is summation. J goes from 1 up to n, x sub j. And vj is summation. I goes from 1 up to m, aij, wi. So I have two finite summations. I'm going to interchange the summations. So instead of summing first over j and then over I, I'm going to sum first over I and then over j, aij xj, wi. And when I do this, I see that this linear combination is a linear combination of the wi's with these coefficients. And I want to show that v1 up to vn are linearly dependent. So I can choose x is not all zero, such this is the zero vector. Now, if each of these coefficients is equal to 0, then I certainly get the 0 vector. So I want to look at the system, summation aij xj, j goes from 1 to n equals 0, for I going from 1 up to m. So let me just write out what this says. For example, when I is equal to 1, This is the equation a11x1 plus a12x2 up to a1n xn equals 0. When I equal 2, this equation says a21x1 plus a22x2 up to a2n xn equals 0. All the way down to the mth equation, I equal to m, I get a m1 x1 plus a m2 x2 plus a mn xn equals 0. So I have this system of, this is a system of how many equations? M homogeneous, or it's a homogeneous system of m linear equations in n variables. And n is bigger than m. That was our hypothesis. And the theorem we proved about systems of homogeneous linear equations, if you have a system of equations with more variables than equations, with n bigger than m, then there is a non-zero solution of this system, x1, x2 to xn. A non-zero solution. So you can choose x's that set all of these equations equal to 0, which means all of these coefficients is 0, which means this is a linear combination of v1 up to vn. Not every x is 0, but this linear combination gives 0, so the v's are linearly dependent. Now, so that's the proof of the theorem. It's, you know, in relatively advanced mathematics, it's hard to understand the proof when you see it for the first time. You see it, you hear it, but the only way to understand it is to find a quiet place and a few hours of time where you can sit down and look at the proof and try to understand it line by line, word by word. And when there's something you don't understand, if it refers to some previous result, then you have to go back and look at the previous result and make sure that you understand it. That really is the fundamental way these things are done. Okay. Maybe just to have a pause for a second, here's a problem. Suppose I give you the vectors -1, 3, and 7, 8. Decide if these vectors are linearly dependent or linearly independent.
Professor, can you put the paper up a little bit?
Yeah.
Thank you.
So -1, 3, and 7, 8. And I'll pause the recording for a moment and give you a chance to solve the problem. So can someone tell me if these vectors are dependent or independent? Let's see. How would we know? Well, we have to look at linear combinations of the vectors. Let me use x and y for my variables, since there are only 2 variables. We want to know what pairs of numbers x and y satisfy the property that this linear combination of the 2 vectors is the 0 vector, right? We want to find x and y that satisfy this vector equation. So this x times this vector is -x, 3x, and y times this vector is 7y, 8y. And if I add these together, I get -x plus 7y and 3x plus 8y. And why I want to know for what pairs of vectors x and y is this equal to 0. So that's the same as solving the pair of 2 equations and 2 unknowns, -x plus 7y equals 0, and 3x plus 8y equals 0. What are the solutions of this? Well, If minus x plus 7y is 0, that means x is equal to 7y. If 3x plus 8y is 0, then 8y is minus 3x, but x is 7y, so minus 3 times 7y, or minus 21y, which means if I bring this over to the other side, 29y has to be 0, which means y has to be 0, which means x has to be 0. So the only solution of this vector equation is x equal y equals 0, and that means that these vectors are linearly independent. Okay. So we have vector spaces, the vector spaces Rn, and we have subspaces. And, we have some intuitive notion. If you look at a line, we think of this as being one-dimensional. Or if you look at a plane, we think of this as being two-dimensional. Or if we look at the space we inhabit, we think of this as three-dimensional. And in general, we want to be able to assign a dimension to a vector space, or to in general, a subspace of the vector space Rn. Like in the plane, if you had this line, that's a subspace. A line going through the origin is a subspace. We would think of this as a one-dimensional subspace sitting inside this two-dimensional space. Or in three space, if we just looked, for example, at the xy plane inside of this three space, we would think of this as a two-dimensional subspace. Or if we took some line going through the origin in three-dimensional space, we would think of the line as being a one-dimensional space sitting inside a three-dimensional space. So the question is, how do we assign, so let W be a subspace? What is its dimension? Right? It would be an interesting thing and a useful thing to be able to say that a subspace is one-dimensional, two-dimensional, or 100-dimensional. Right? That's the idea. And we start with the following very important theorem. So I'm now looking at section 1.7, which has to do with bases and dimension. So we have, let's say, this vector space V equal to Rn. These are the n-dimensional column vectors. And let S be a non-empty subset of V, and let W be the subspace generated by S. So this is the set of all linear combinations of vectors in S. And the theorem says that there exists a linearly independent subset of S that generates W. Let me give an example. Suppose V is R2 and S is the set of vectors 1, 2, and -3, -6. So what is the subspace? So let's call this W1, and this is W2. So if a vector W is in the subspace generated by S, which I'm calling W, then W is some linear combination of W1 and W2. It's x1 times 1, 2 plus x2 times -3. Let me just to make this one, I'll make this 2, 4. 2, 4 and -3, -6. So W is this linear combination of these two vectors. But W1 and W2 are linearly dependent. Because if I have the vector 2, 4 and the vector -3, -6, if I multiply this by 3 and this by 2, I get 6, 12 -6 -12 is 0, 0. So here's a linear combination of these two vectors that gives the 0 vector. So these two vectors are linearly dependent, they're not independent. And in fact, if I take any linear combination of these two vectors, let me write it here. If W is xW1, x1W1 plus x2W2, that's x1 times 2, 4 plus x3 times -3 -6. But actually, from this expression, I can see that -3 -6 is -3/2, 2, 4. If you do the arithmetic, -3/2 times 2 is -3, -3/2 times 4 is -6. So this is x1, 2, 4, -3/2 x2 times 2, 4. This is just some linear combination of the vector 2, 4. So W is spanned by just this one vector 2, 4, and one non-zero vector is always linearly independent. Okay. And the theorem says this very simple phenomenon always holds. So if S is not empty, then S contains a linearly independent subset S1, maybe not S1, what should I call it? S prime, such that S prime generates exactly the same subspace as S. How do we prove this? So let's start with this first case, case 1. Suppose S is a finite set. So S consists of, let's say, k vectors, W1, W2, up to W sub k. And every vector in the subspace is a linear combination of these. So if one of these vectors is 0, of course, we can throw it away. We don't need it. This is a finite set. It has only finite many subsets. So you can look at all the finite number of subsets, and some of them are linearly independent. So suppose we let S prime be a maximal linearly independent subset of S. That means that if S prime is contained in T, and T is also linearly independent, then in fact S prime equals T. There's no bigger set contained in S that's linearly independent, bigger than S prime. Okay. So suppose we let W prime be the subspace generated by S prime. So this is contained in the subspace generated by S, which is W. Suppose they're not equal. Suppose W prime is different from W. That means here we have W, and sitting inside of W is W prime, and they're not equal. If they're not equal, there's some vector W, which is in, or maybe I should call it V, just to have a different letter. There's some vector V, which is in W, but not W prime. So then there exists a vector V, which is in W, but V is not in W prime. In that case, I claim that S prime union this V is also linearly independent. Why is that? Actually, it's a good question. Maybe that's not a good way to do this. So suppose, so let's say S prime consists of the vectors, say W1, W2, up to W sub L. And we have some linear combination, X1, W1, X2, W2, XL, WL, plus let's say Y times V equals 0. If Y is different from 0, then YV is minus X1, W1, minus X2, W2. I'm just putting this on the other side of the equation, minus XL, WL. If Y is different from 0, I can divide by Y, and I get this. So then V is a linear combination of the W's. So it's in the subspace generated by this set of W's, which is false, because we picked V not to be in this set. So therefore, Y has to equal 0. But then X1, W1 up to XL, WL is 0. So all of the X's have to be equal to 0 because the W's are linearly independent. So that means that the set S prime union V, which is W1 up to W sub L, union V, is linearly independent. Actually, this is not a bad proof, but I'm going to change it slightly. Okay, so let me do this a slightly, what I call a more elegant way. So suppose S is a finite subset of my vector space Rn. And I let W be the subspace generated by S. And then let S prime be a maximal linearly independent subset of S. If S prime, in fact, is equal to S, we're done, because S is a linearly independent subset of itself and it generates S. Suppose S prime is not equal to S. So let's say S prime is W1, W2 up to W sub L. For some L strictly less than K. So again, I have the same picture. Here's the subspace W generated by S. Sitting inside of that is the subspace generated by S prime. Suppose I let I be some number from L plus 1 up to K, and I consider the vector Wi. If Wi is not in the subspace generated by S, so if that Wi is out here, then by the argument I just gave, S prime union Wi must be linearly independent, which contradicts the maximality of S prime as a linearly independent subset of S. So therefore, Wi is in the subspace generated by S prime, which means all of S is in the subspace generated by S prime, which means the subspace generated by S is contained in the subspace generated by S prime, which is certainly contained in the subspace generated by S. So in fact, I've picked a linearly independent subset S prime of S that generates the whole space. And that's, in fact, what I wanted to prove. Oh, okay. Again, this is a lot to think about. And fortunately, we have the weekend coming up, so you have 3 days to try to think about this. Again, I remind you, I have an office hour tonight at 7, tomorrow afternoon at 5, and I'll probably have one on Sunday, just so you have a chance to ask questions if you want. So we now introduce the following definition. A set S of vectors is called a basis for a subspace W of V if, first of all, S generates W. So every vector in W is a linear combination of vectors in S, and S is a linearly independent set of vectors. So for example, if we take R2, I can take S to be the set of vectors 1, 0, and 0, 1. So these are linearly independent, and they generate R2. So this is an example of a basis. In R3, I could take S to be the 3 vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is a basis. In R3, this is one of the homework problems. I could take the 3 vectors 0, 1, 1, 1, 0, 1, and 1, 1, 0. And this is a different basis for R3, and so forth. And what we just proved is that every vector space has a basis. Right? Given any set of vectors that generates the space, in fact, it contains a subset that's linearly independent, and so it forms a basis. So for any set S, or for every set S, what is called the cardinality of S is the number of elements in S, and it's denoted by S with absolute value signs. So if I took a set containing one cat and one dog, the cardinality of that set is 2, because this set has 2 elements, cat and dog. If I took the set 7, 11, and minus 19, the cardinality of that set is 3, because there are 3 elements in the set. If I take the set 1, 2, 2, 2, the cardinality of that set, well, the set 1, 2, 2, 2 is the same as the set 1, 2. In a set, as you're looking at the number of different elements in the set, the cardinality of this set is 2. Right? This is the same as the set 1, 2. So the only elements in the set are the numbers 1 and 2. So this set is cardinality 2. So this is our notation for the number of elements in a set. And here is a very big theorem. I'll give it a star. It says that W be a subspace of V if B1 and B2 are bases for the vector space V, then they have the same number of elements. The cardinality of B1 equals the cardinality of B2. So you have a subspace. The previous result shows that it has a basis, and the theorem says that every basis, all bases, have the same number of elements. Why is that? So well, let me just look at the theorem. And the proof that I put in the notes. So proof. The set B1 generates the subspace W. And so every vector in B1 is every vector in W is a linear combination of vectors in B1. we have B2 is contained in W. So every vector in B2 is a linear combination of vectors in B1. And our theorem we proved earlier says that if you have a subspace generated by a certain set of vectors, so our subspace W is generated by B1, and the number of elements in that is just the cardinality of B1. If you take any linearly independent subset of that subspace, it has no more than this number of elements. Well, B2 is a linearly independent set contained in W, so the number of elements in B2 is less than or equal to the number of elements in B1. And then you can reverse the argument, interchanging B1 and B2. You get the number of elements in B1 is at most the number of elements in B2, which means the number of elements in B1 equals the number of elements in B2. And that's all there is to the proof. So given a subspace, there's a unique integer, a non-zero subspace. You have a unique positive integer, which is the size of a basis, and it doesn't depend on what basis you choose. So the dimension of the subspace W, which we denote by dimension of W, is the number of elements in a basis, the cardinality of a basis. And so this is a truly fundamental result in linear algebra. If you take any finally generated subspace of a vector space, it has a base, it has a dimension. Has a dimension. All right, well, I think this is a lot to digest, and I think maybe I will stop at this point. I basically covered essentially all of the first chapter of the notes. And this is a lot of material. So we squeezed it into a week because this is summer school. And summer school, a day is a week of the regular semester, and a 4-day summer school week is a month of the regular semester. And the difficulty in summer school is, for a course like linear algebra, is it takes time to absorb the concepts. And time is a very rare commodity in summer school. So you really need to be spending time every day trying to understand what they're doing. And I encourage you to come to these sort of drop-in problem session office hours and ask questions. And that really is the best way you will learn to understand the material. Okay. Any questions before we end for the morning? All right, again, let me remind you, I'll be online tonight at 7, tomorrow afternoon at 5, and I'll also figure out some time on Sunday when I can also be available. Okay.
Professor, I have a quick question.
ahead.
Do we use the same link for the
Yeah,
tutoring
it's the
hour?
same link for everything.
Okay, okay. Thank you.
And just remember, don't breathe the air.
I know, it's terrible.
You know, they closed the campus. If we were meeting on campus, no classes are meeting on campus today.
But I'm glad. I mean, I don't know why they didn't cancel yesterday though. Yesterday was worse, I think.
I think they canceled in the afternoon. They kept it. It took
Okay.
them a long time to make a decision, but at some point around 2 or 3 o'clock, they told everyone to go home, and they would be on Zoom if possible. I mean,
Yeah,
we're
that
so
that
lucky that we're always on Zoom, so there's no
thank God.
but yeah. Uh,
Good though.
yeah. Okay, anyway, be well. Hope to see
You
you
too,
soon.
Professor.
Bye.
I'm gonna continue watching the videos. It's a lot.
It is a lot. I think it's very hard. I personally think summer school is crazy for mathematics.
Yes.
It might be for
Yeah.
other subjects too, but in math, there's just so many concepts you have to absorb.
Yeah. Yeah.
And
Oh, goodness.
it sometimes can take weeks, but in summer school, you don't have weeks. The whole summer school is 4 weeks.
Yeah.
So makes it tough.
Professor, when are we gonna have our midterm?
A week from today.
Okay.
Right, that was posted before even the semester started. The midterm is Thursday the 15th. The final exam is Thursday the 29th.
Okay.
That's the university schedule. I mean, I don't even have any choice about that. The last day of class is Wednesday the 28th, and
Yeah.
Thursday the 29th is for all final exams.
Okay.
All right.
Yeah.
Okay. All right,
Thank you
bye.
so much.